about rigid body equilibrium, and we're still discussing 2D. I'm going to start rigid body equilibrium 3D today, okay? But let's do one more 2D problem, and then we'll discuss, get to 3D, and then on Wednesday we will also do more on 3D. Okay, so let me do an example, and the reason I chose this one, because this in a way gives you an idea or sort of paves the road for next theme when we get to that, which is frames. So I want to do this problem in two different ways, although the concept is the same, but just to demonstrate more in-depth sort of the understanding of free body diagram of a rigid body. So let's say you have an object that is fixed here, supported through a fixed end support here. As you can see, no rotation allowed, no translational motion along X and Y. Then you have two pulleys here connected to this structure. Okay, so let's see. Let's do it this way. One pulley here, one pulley there. Okay. This is 2 meters. This is 1 meter. And let's say this distance is 3 meters. And a cable is attached to a weight of 20 Newton that goes around this pulley, the second pulley, and it is connected to the wall, okay? So that's how this structure is carrying this 20 Newton load. It's not directly handling it, but through this pulley system. And what the problem is asking you to find all the external reaction forces. So find basically reaction forces at C. That's what the problem is asking you. Step one, easy, right? Draw an XY coordinate system. So this is XY. Step two, we want to draw the free body diagram of the structure. I will consider the structure consisting of, okay, this is A, B, C, of this bracket that is supporting those pulleys and this structure. That's how I will address the problem first, or solve the problem that way. In other words, I look at the structure being just this bracket. So I need to know what are the external reaction forces and what are the applied forces on the structure. The structure, if it is considered that way, it is fixed here, right? So there will be a moment, built-in moment at C, that is resisting the motion, a vertical force Cy and horizontal force Cx, right? That's what that fixed end support represents. That clear? No problem? Okay. Now, so how these two pulleys that are attached to the structure and handling this load affect that structure in terms of the load that they exert on that structure. So in order to understand that, let's look at the free body diagram of each pulley. This is pulley A. This pulley A is subjected to a force of this cable, 20 Newton at this end, obviously this cable is going around the pulley, so the same force of 20 Newton would be acting that way, right? And by the way, if you connect these two, this would be obviously 1 meter. The radius of these pulleys are given as 0.5 meters, okay? So let's say this angle alpha in this triangle, you can find it, which is this angle. We'll find it in a minute. But let's first set up the free body diagram of this pulley. At point A, this pulley is supported by this pin at A, right? That means there are two unknown forces like this, AX and AY, that are holding this pulley in place. But where do these forces come from? These forces are coming from the pin that is holding this pulley in place. So there will be forces equal in magnitude, opposite in direction, acting from the pulley over the pin, and the pin is sitting on this structure. So what that means then, at point A, you have forces equal in magnitude and opposite in direction should be acting at point A on the structure, right? Is that clear? Any questions on that? Because if these are the forces coming from the structure acting on the pulley, third law of Newton, right? Action and reaction. Reaction forces, which are equal in magnitude, opposite in direction, should be acting from the pulley on the structure. So that's the free body diagram of the structure at that point. Same thing with pulley B. You have a force of 20 Newton here and a force of 20 Newton here. And at point B, you also have a force of By. I don't know what the direction is, I'm just assuming. And a Bx like this, acting. So if I make that assumption, then at point B, I have a force of Bx this way and a force of By that way, acting on this structure. But what are those forces? I can find them actually. Why? Because if you look at the free body diagram here, first of all, I can resolve this force into its components. So let me do it in a different color. So I will resolve this force into these components. This angle is alpha. From here, you see that tangent of alpha is 0.5 over 1. So if tangent of alpha is 0.5 over 1, I believe alpha comes out to be 27 degrees. If you could double check that, that would be great. That's okay. So can anybody double check while I'm going through this? Somebody. So if that's the angle, so if I write, let me call this free body diagram 1, this is 2, and this is 3. So for that pulley then, I can write summation of forces along x is equal to 0. So you have negative ax, right, plus this, which is 20 cosine of 27, right? That's this force, and that's it, is equal to 0. So ax would be, 20 cosine of 27, so it would be 20 cosine 27. So how much would be ax? Can somebody give me that? Should be about 17, 18. 17.8. So let me say 18. Acting. So the assumed direction was also correct. So this is 18 Newton. I write summation of forces along y is equal to 0. So I have AY, right, minus 20, this force, and then minus this one, which is 20 sine of 27 equal to 0. So AY would be 20 times 1 plus sine of 27 equal to 0. So it would be 1.5 times, almost 30, right? Or how much? 29, great. So AY would be 29 Newton. Again, the assumed direction is correct. So this is 29 Newton. Now let's go to this one. Again, this is alpha. So if I resolve this into its components, I can write for 2, I can write summation of forces along x is equal to 0. So I have 20 Newton minus this, which is minus 20 cosine of 27, plus bx is equal to 0. So bx will be 20 times cosine 27 minus 1, right? So that'll be almost 2.1. Can somebody give me that number? Cosine 27 is about 0.8, 0.9 minus, yeah, something like that. How much?
Negative 2.17.
2.17, how about 2.2? Negative 2.2 Newton. So this negative sign means the assumed direction here is wrong. I have to change that, and the negative means that obviously that is correct, wrong. So get rid of that. This is the actual bx acting on this. So next one, summation of forces along y is 0. I have by, right, plus 20 sine of 27, right, and that's the only force I have, is equal to 0. So by would be negative 20 sine 27. So that should be what, about 9? 9. So, and this one is, again, negative. That means the assumed direction here is wrong. Or this one should also change. So that is by is 9 Newton. So this is 9. Bx was 2.2 Newton. So now you have the free body diagram with all applied loads, externally applied loads on this structure, right? Or if you want, I can do a clean one here. So this is C, where you have this unknown moment, unknown vertical force, unknown horizontal force. You have 2.2 Newton here. You have 9 Newton force in this direction. You have 18 Newton force in this direction, and you have 29 Newton force in this direction. In other words, the effect of having those pulleys as a weight on the structure are these force sources, okay? So we have the complete free body diagram of the structure now, and now we apply equations of equilibrium to this free body diagram, starting with summation of moments at C equal to 0, so that I can get rid of these two unknowns and find the moment first. So I have MC, which is assumed that is going to be negative, positive in this direction, so this is negative clockwise. These two forces create a counterclockwise moment, and the moment arm, this distance is given 3 meters, so I have plus 2.2 times 3 plus 18 times 3. This one generates a clockwise moment. This is the distance given as 1, so you have minus 9 times 1, but this one generates a moment counterclockwise. Moment arm is 3, so plus 29 times 3 is equal to 0. So let's see, this is 54 minus 9 plus 87 plus 6.6. So I have almost 60 minus 9. That's 51, right? Plus 87, 50, yeah, 50. Okay. 1 and 80, 137, 138, something like that. So anyway, this comes out to be a positive, right? So in other words, MC would be 138 Newton meter, and it turns out that the assumed direction is correct, that is acting in this direction, because the result of this would be positive answer for MC. So once you have that, then now summation of forces along X equal to 0, so you have 2.12 plus 18 minus CX is equal to 0, so CX would be 20.2 Newton, and the assumed direction is correct. And then summation of forces along Y equal to 0, so you have 9 minus 29, okay, plus CY is equal to 0. CY comes out as almost 20 Newton, again positive, so the assumed direction is correct. Okay. Any questions? Yes?
Why do you draw the vectors on the pulleys like opposite to the vectors that you draw on the main free body diagram?
See, as I said, if this is the free body diagram of, say, pulley 1, right, pulley at A, this is a pin, so we know that two forces are supporting a pulley, one this way and one this way. If I assume these are the directions for those forces, where do these forces come from? From the structure. That is, these are the forces from the structure that are holding this pulley in place, right? When two objects are connected or in contact, right? Remember the third law of Newton. Whenever two objects are in contact, they exert forces that are equal in magnitude, opposite in direction to one another. So if these forces come from the structure, acting on the pulley is exerting forces equal in magnitude, opposite in direction onto this structure. That's why AX on the structure should be the other way, this one should be downward. Does it answer that clearly? Yes.
So that what's called a reaction? So it asks
The
for
third law of Newton.
No, it's saying like to ask for the reaction, is that like you're looking for the pulley force on?
Reaction, yes, these are the reaction forces.
Gotcha.
Or support reactions, or connection forces. They are all the same.
Okay.
Right, yes.
On tests, do we have to do the full process, or can we just bypass it by saying like the external forces are?
Good question. What you're alluding to is that, is there another way to solve this problem, right?
Well, just taking out the AX, AY, BY, BX on the actual pulleys and just saying the 20 newtons on the pulleys equal to whatever AY.
Let me actually explain that. But basically what you're asking, or you're trying to ask or say or question is there another way to do this problem, right? And that's exactly what I like to do. I did it this way first because I wanted to, just focus on the free body diagram of the structure that is our interest. So if you're isolating that structure, anything that is attached to it, I want to remove it, just focus on the free body diagram of that structure. So these pulleys, I did not consider them being as part of this structure. I take them out, so the effect of taking those out means putting some forces back, which is what I did. But there's also another way that you can look at the same structure, right? And that's like this. If you assume that these pulleys are an integral part of the structure, you do not want to cut them, right? These are part of the structure. In fact, I'm going to ask you that as a question, because that's the question I asked in the other class. This structure is holding a load of 20 Newton, right? So if these pulleys are part of the structure, and we want to find the external forces acting on this structure, how do we do that? How do we draw the free body diagram? Now, I'm not going to take the pulleys out. Leave them in there. So what is my structure now? The structure would be what? The structure would be this, and these two pulleys, right? And I only need to cut the structure from what is supporting it. So the structure is supported here and here, right? So you have this cable going around, right? So I would cut it here, and I would cut the structure here. So still, I have these forces, right? But here, if I cut the cable here, is now, everything is integral part of the structure. I'm not going to cut this cable here. I will cut it only at the point that is connected to the wall. So, in other words, I will have then, in this case, as a result of cutting this, I have a force of 20 Newton here, and a force of 20 Newton here. That's another way of solving the problem. In other words, this is an alternative free body diagram. I assume that these pulleys are attached to the structure. I'm not going to take them out, so I will consider my structure as being that bracket and the pulleys all together. So that's, I think that's what you're, yes. Okay. But intentionally, as I said, I did it that way because first of all, I wanted to just look at the structure without the pulleys, considering that as my structure. And second, I wanted to show you sort of a way of doing the free body diagram for pieces of the structure, which kind of paves the road for the next topic, which is the frames. Any other questions? Okay. So with that said, I'm going to now introduce the next, not a next new topic, but extension of this rigid body equilibrium of 3D structures. So, 3D equilibrium of rigid bodies. The only thing that changes in the case of 3D rigid bodies is this. In the case of 2Ds, the supports that are holding the structure in place have no more than three basically functions. The resisting the motion, translational motion in X and Y, and rotational motion, which is only one direction, right, about Z. So we had this type of support, regardless of basically their shape or, the way they are attached to the structure or their configuration, they either resist motion in one direction, two direction, or three directions. In 3D, in general, right, you can have translational motion in X, Y, Z direction, and you can have rotation about any of these axes, right? So if you think of the number of potential directions of motion, there are 6. So you can have up to 6 unknowns at a support, right? Of course, that's a maximum number. So in general then, you can have up to 6 unknowns versus 3D that you can have only up to 3 unknowns. The sort of the functions of course, these kinds of supports is quite different from 2D, and in fact, their names, their shape, and so on are also a little bit more complicated. It's not easy to simplify them as just a roller and a hinge and a fixed end support. There's a good table in your book. If you look at, in fact, the front page, right on the back of that, there's a table that is also table 410 in the chapter 4 that tabulates these various types of support you may come across. A ball and socket joint, a journal bearing, a fixed support, and so on and so forth. That each represents basically how many directions motions is allowed. For instance, a ball and socket joint is equivalent to a simply a roller in 1D. Rotation in all directions is allowed. Translational motion in any of those directions is not allowed. So there are 3 unknowns. And so with that said, the only thing that really is different is that, first of all, step 1, which is setting up the coordinate system, this is always given. Usually when you're given a 3D structure, coordinate systems are set up. Step 2, okay, is the same. You still have to set up the free body diagram with the understanding of what functions each support system represents. And typically you are given either enough information or you're directly told that, for instance, on joint C, there is only one unknown, or this joint C does not allow motion in X direction. Usually, either implicitly or explicitly, you're given that. So you're set up the free body diagram. And the third step number 3, is you have 6 equations of equilibrium. Now, summation of forces along X, Y, and Z is equal to 0. Or you have summation of moments is equal to 0. When it comes to summation of moments in 2D, I said that the easiest way, in fact, to approach these problems is you start with summation of moments because you can take summation of moment about the point of intersection of 2 unknowns, get rid of those. The equivalent of that in 3D, what I recommend, you don't have to necessarily follow that, but would be summation of moment about an axis is equivalent to that. In other words, you know that you can always find an axis that intersects with more than 3 unknowns. So you can, if you consider that axis, you can get rid of up to sometimes 5 unknowns. You end up with only 1 unknown left. Solve for that, and then go and apply other equations. Either that, or you just simply use summation of moments about each of the axes, all forces known and unknown. So you have 6 equations, 6 unknowns, and you solve for those. So let's demonstrate this through an example. Does anybody have a copy of the book? I didn't bring mine. If I can borrow your textbook. Do you have a textbook with you? You do? Terrific. I'll just borrow that. Boy, your deck was so heavy duty. Okay. See how, okay, let me do a good problem. I know it's here. Okay. Here it is. I'm going to do problem 4106. It's a good problem, a good example to start with. This is what the problem looks like. You have a pole like this that is supported at the bottom with a socket joint that is something like this, that the rotation in all three directions is allowed. This joint cannot move along X, Y, or Z direction. That's what it is, right? So the structure is supported this way. You have a force of 455 through this cable, comes here, connects this structure to a point F on the ground. Coordinates of F are given as, okay, 3 meters, or actually -3. Let me just write it down. -3, Y of 0, and Z of also 2 meters. Then, so there's a force of, we know that there's a force of 455 Newton in this cable. Then there are two other cables that are attached to this structure, that is point B, and connect that point B to these 2 points on the ground. Coordinates of these are also given as 1.5, 0, and 3. This 1 point D is given as, okay, X of 1.5, Y of 0, and Z of -3. Point B is simply at 3 meters above the ground, so 3, 0, and this point C is at 6 meters above the ground, okay? This is 0, 0, 0. So the problem is asking you to find, okay, that was yours. Thank you. So what you've been asked to find is forces in cables BD and BE and at A. As I said, at A, you are told that there's no rotation. Rotation is allowed in all 3 directions, so that support is only resisting motion in X, Y, and Z direction. And these are 2 cables, okay? So step 1 is given, right? Step 1, you do have the X, Y, Z coordinate system. All these, you're given that. Step 2, you need to set up the free body diagram. I'm not going to redraw this, both to save time and also is easier to do it that way, at least here in class. So concept is the same. You need to free the structure from anything and everything that is supporting it, right? So if I release this at point A, or remove this support at point A, what this point represents are 3 forces that are resisting motion in this direction, and in this direction. So I would just simply call them, okay, AZ, AX, and AY. If I cut this structure, cut these from these two cables, so what these two represent is you have a force of B, D, and a force in this one, force of B, E. And obviously, this one, which is the force of CF given. So you have 5 unknowns, and you want to find all those 5 unknowns, okay? As I said, I prefer this approach myself, that I like always to find the easy way, as I've told you before, easy way out. So I want to get rid of all the unknowns except for one. How do I do that? When you want to get rid of as many unknowns as possible, think about an axis that intersects all those unknowns. Because if you have an axis that intersects with a force, that force does not make any moment about that axis. So can you think of a possibility?
One axis.
If I consider y-axis intersect with all the unknowns, so you have nothing left. Because it intersects with this, intersect with these two, intersect with all 3 of them, they're all gone. So that equation is not going to be much use. Any other possibility? How about if I consider something like this? Summation of moments about A, D. How many unknowns do I end up with? Just the force BE, right? Because I have the magnitude of this force. So I end up with one equation, one unknown, right? So as you see, 3D problems are not difficult. It's just, it's kind of more tedious. Takes a long time, the process, because you have, more algebraic equation to write or derive, right? So what does summation of moments about AD mean? These 3 forces don't make any moment about AD. This one doesn't. So you just simply have the moment of the force BE about this axis AD, right? And you end up with the moment of this force of 455 Newton about AD is equal to 0. And you know, before you start, that you have only one unknown in this equation. But you need to set this up step by step. So what do I mean by that? Moment of FBE about AE is what? What is the moment of a force about an axis? Is the moment of that force about a point along that axis, right? Dot product of that and the unit vector of this axis, right? So the easiest point to consider along this axis would be point A. So if I want to find moment of this force about point A, right? And then I need to find the dot product of that and the unit vector of AD, right? So let me put this as 1, this is 2. So this is part 1. But then you have to break this down. First of all, you need to set up the unit vector of AD, which is not difficult. You have all these coordinates, so it would be 1.5i, 0 minus 0j, minus 3 minus 0k, divided by 1.5 squared plus 3 squared. So that is the unit vector, right? Then you need to find the moment of force BE about A, right? That is position vector from that A to anywhere along this cable. So what position vector is best to consider? Yes, you said it. It would be AB cross the force BE, right? This is what? This is just simply 3J cross equation now for this force, which is of course unknown. So it's F of BE, unknown, times the unit vector of that force, BE. Again, I have these coordinates of a tip and the starting point. So would be 1.5 minus 0. You have to write the unit vector for that, right? So it would be 1.5 I, 0 minus 3 J, then 3 minus 0 K, divided by 1.5 squared plus 3 squared plus 3 squared, right? Let's figure this out. You end up with this determinant, right? You have F, let me just call this F of BE. So this is I, J, K, right? Position vector is 0, 3, 0. And could somebody give me this quick? If you do that, you don't know what a good you've done to humanity. Everybody will be happy. So just give me this. If you give me this, it's good enough.
4.5.
How much?
4.5.
Terrific, 4.5. Great. So now, this is actually easy then, right? So this would be 0.3, right? I minus 3 over, or 1 over 1.5 would be 2/3 of 0.67 J and plus 0.67 K. Great. So would be 0.3 minus 0.67 plus 0.67. Okay? So you perform this operation, you end up with a vector equation, right? For I, you will have 3 times 0.67 or 2 point, almost, let's say 2. I'll simplify that. So it would be 2I. For J, it would be 0. For K, would be minus 0.9 K times F. So this is the moment of that force about point A, right? Now you need to find the unit vector, the dot product of this and this unit vector, right? So this moment of F BE about A D would be what? Would be 2 times, you only have this, right? So you have 2 times 1.5 over, what is this one? This square root. 9 plus 2.25, 11.2, square root of 11.25. 3.4. So this would be 3. So that's that, right? That's I times I, right? J times J, there is no J. Then K times K. So I will have 0.9 times 3 over 3.4. So that would be the moment of this force that you have also F. So a moment of F of BE about AD would be F magnitude of BE times this, right? So this was part 1. Now you need to find moment of this 455 Newton about AD, right? So you need to find moment of that 455 Newton about A first, right? And then dot product of that and the same unit vector AD. But what is this? You need position vector times that. Position vector is 6J. You need to write the vector equation for that. Write that determinant. So this would be 6J cross 455 times the unit vector of CF, right? Then you find that, find the dot product of that and this unit vector. Turns out to be a number, right? Add those up, equate them to 0, you find the force in B. So as you can see, and I promise, in 3D, the only thing that is different, you have a lot more derivations and operations. It's just more algebraic work to do. The important thing is, though, remember the concept. What does summation of moments about an axis mean? Or what is the moment of the force about an axis? Which is going to be your next exam, by the way, right? Moment about the force about an axis, you find the moment about a point, and then the dot product of that, and the unit vector of the axis. Yes?
Well, this is going to be on the exam as well.
On the upcoming exam, you have the moment about an axis, equivalent systems, 2D rigid body equilibrium, plus all Wikipedias in the world. Because you have 6 points, bonus points also, on this exam. Half of it is on current events, the other half about US history and the world history. How about that? Okay.